everyone. So in this video we will try to find out the directional derivative of this function fxyz. So this is a function of three variable and it is a scalar value function along this vector minus 1 comma 0 comma 1. So let us recall the definition of directional derivative. Suppose we have a function of n variable, scalar value function of n variable fx1 x2 to xn, and we have to calculate the directional derivative along some vector v, which is given as a1, a2 to an. Now, if v is not an unit vector, what we have to do? We have to normalize it first. So we have to do this calculation v by norm of v, which we can do, so that the norm of this vector will become 1. Now, for make the computation easier here, so we are assuming that the vector which we have started with is actually a unit vector. So let us assume that this v is unit vector. So what we have to do to calculate the directional derivative? We have to see the increment of this function along this vector. So basically we have to take x1 plus ha1 comma x2 plus ha2 and so on. Basically we are adding this x1 to xn plus h of v. We are finding this functional value at that point. So this is xn plus han, and to find the inclination we have to subtract the functional value at x1 to xn, and then we have to divide it with h, and we have to calculate the limit of this function as h tending to 0. So this is the definition of directional derivative along this vector. So here in the given example, so if I try to solve this problem, so our v is given as minus 1 comma 0 comma 1. So let us normalize it first. So we have to do this thing first, v by norm of v. So v is minus 1 0 1, and norm of it is basically 1 plus 1 and root over of that, so it is root 2. So the normalized vector, the unit vector along this direction is 1 by root 2 into minus 1 0 1. So this is our unit vector. Now what we have to do? We have to apply this definition. So let us apply this definition. So our fxy is given as x square y plus y square z, and the unit vector which we got here is 1 by root 2 minus 1 0 1. So now we apply the definition here. So we have to calculate limit h tending to 0 f of x minus h by root 2. So because I have to multiply h with this and then add this, so the first coordinate will be x minus h by root 2. The second coordinate will be y, because in the second coordinate of the vector there is 0, and in the third coordinate there is z plus h by root 2, and I have to subtract fxyz here and divide it with h. So I have to calculate this function, and basically I have to calculate this limit. So if I start to calculate this limit, so for the first function what I get, it is x minus h by root 2 whole square into y plus y square into z. So z is here, z plus h by root 2. So yeah, and what was fxyz? That is our given function x square y minus y square z. X square y plus y square z, there is a minus sign outside, so I am getting minus x square y minus y square z, and I have to divide it with h. So if we break this up, we get limit h tending to 0. This is x square y minus 2 x y h by root 2 plus h square y by 2 plus y square z plus y square h by root 2 minus x square y minus y square z, and there is h in the denominator. So if we see this x square y and this minus x square y get cancel out, and this y square z and minus y square z will cancel out. So the remaining term, if we write it, it is nothing but limit h tending to 0. So the first term, this h and h will cancel up. So I am getting minus 2xy by root 2 plus h y by 2 and plus y square by root 2. Again in this term h got cancelled out. So there is only one term where h is there, and as h tending to 0, this term will go to 0, and the remaining terms are independent of h, so those will remain as it is. So what I get minus 2xy by root 2 plus y square by root 2. So this is the directional derivative along the vector which we want to calculate. Now there is another theorem which is saying that if we calculate the grad of this f, and if we take the dot product with the unit vector along which direction we want to calculate the directional derivative, then also we will get the same result. So grad of f means we have to calculate fx, fy and fz. Basically this vector which consists of the partial derivative along each axis, and here our unit vector which we have already calculated, this is 1 by root 2 into minus 1 0 1. So if we calculate the partial derivative, so recall what was our function. Our function was x square y plus y square z. So what was our fx? Fx is 2xy. What was our fy? Fy is x square plus 2yz. And what was fz? Fz is y square. So if I write this down here, 2xy, x square plus 2yz, square plus 2yz, and y square, if I take dot product with 1 by root 2, so this is minus 1 by root 2, 0, 1 by root 2. I am taking 1 by root 2 inside the vector. So if I calculate it, I will get minus 2xy by root 2 plus y square by root 2. The middle term will contribute 0 because there is 0 here in the second coordinate. So y square by root 2. So it is exactly the same thing what we have calculated above. It is exactly the same thing what we have calculated here. So here definitely we can calculate the directional derivative using this method, and also we can verify that when we are using the definition, we are getting the same directional derivative. Thank you.